Good day, everybody. This is Chris back again with the Ancient Scholar, and today what I'm going to be talking about is a transition in biotransformation. So up to this point, we've been talking about phase 1 biotransformation reactions, and these phase 1 biotransformation reactions pretty much involve monooxygenation, adding oxygen. Okay, so we're oxidizing a xenobiotic. In many cases, doing that through the agency of adding a hydroxyl group, and hydroxylating our xenobiotics tends to make them a bit more polar, and that makes them easier to eliminate via the urinary tract for the most part, and it may detoxify them and may even cause the creation of toxic metabolites depending on what we're dealing with. This general process can be done by a few different types of enzymes, or catalyzed by different types of enzymes. Of course, the first and one of the most significant superfamilies of enzymes we talked about were the cytochrome P450 oxidase microsomal enzymes. We also talked about a rather minor set of enzymes, the flavin monooxygenase enzymes. And then we also talked about the hydrolase enzymes, the hydrolases, of which there are multiple lipases. We had lipases, we had carboxylesterases, and so on and so forth. So these all three are very large families of enzymes, and they are all involved in phase 1. And in general, they involve a redox. They involve catalyzing a redox reaction, often adding an oxygen. And there you go. Okay. So now what we're going to do today is we're going to start talking about the phase 2 biotransformation reactions. And phase 2 biotransformation reactions are often either go by either conjugation, conjugation, or synthetic reactions. Now, the phase 2 biotransformation reactions differ from the phase 1. In the phase 1 reactions, we were either adding or unmasking very small polar oxygenated groups, hydroxyl groups primarily, involving some of the hydrolase enzymes. We were also making carboxylic acids, or converting the xenobiotic into a metabolite that contained a carboxylic acid functional group. Phase 2 biotransformation reactions involve the conjugation of larger molecules. I know most sources will say that it involves adding small molecules, but when we talk about a hydroxyl group, most molecules are going to be rather large in comparison to a hydroxyl group. So I say the term large, but just keep that into context that we're not that phase 2 biotransformation reactions don't involve conjugating really large complex proteins or anything like that, but it does involve the conjugation of larger molecules than you would see in phase 1 biotransformation reactions. So these conjugation reactions are catalyzed by enzymes, and in these enzymes, the broadest way of looking at them, we can call these enzymes transferases because they catalyze the transferal of these conjugation groups, or these conjugation products, if you will. So in general, we can call these enzymes transferases. Transferases catalyze these reactions. So I think it's important to talk about what the general types of reactions uh, are, or that we deal with. So probably the most common and most relevant reaction from a toxicological standpoint is something known as glucuronidation. So I'll just write that up here. All right, glucuronidation is the conjugation of a glucose. It's a modified glucose molecule or dextrose molecule, and I'll talk about what exactly the modification is, because it's not like a D-glucose that you're used to dealing with. There is an acidic modification that occurs to that functional group that we'll talk about. But in essence, you're adding a modified glucose molecule to the xenobiotic. Another reaction is sulfation. All right, so adding a sulfur-containing group. We could also have acetylation. All right, so instead of breaking breaking up acetyl groups, we're adding acetyl groups. We can also add methyl groups, what's known as methylation. And in general, the conjugation reactions involve adding a polar group. The modified glucose, the sulfate, the acetyl, these tend to be a bit more polar, but just know that methylation, methyl groups tend to not be polar at all. They tend to be nonpolar. They tend to be lipophilic. So there are always exceptions to these rules of thumb that we talk about. And then we have conjugation with amino acids as well. Amino acids. And then finally, maybe I'll put it down here, we have conjugation reactions that involve glutathione, conjugating glutathione. Okay, so these are the major molecules that are added, that are attached to the metabolites or the xenobiotics. And what I'm going to talk about primarily today is glucuronidation. This is very important, very common, and highly relevant in a toxicological sense. Okay, so in most mammals, glucuronidation is a major component of phase 2 biotransformation. Interestingly enough, it does not appear to be a major pathway in cats. And this in part explains why certain drugs can be highly toxic in cats that aren't nearly as toxic in most human beings at therapeutic doses. For example, a major way that acetaminophen is biotransformed, over 90% of the acetaminophen biotransformation involves glucuronidation. In fact, I'm going to show you how that works here in a minute to give you an example of a glucuronidation conjugation catalyzed reaction. However, because cats do not have well-developed, as far as I know, as far as I'm aware, do not have well-developed enzyme systems that can successfully perform glucuronidation, giving a cat something like acetaminophen would be exceptionally harmful to that cat. That's just a kind of an aside, but it just shows you how you can have these differences. But with that in mind, in human beings, and I presume primates, question mark, glucuronidation is a pretty significant way, particularly when it comes to endogenous substances like bilirubin. From red blood cells are broken down, a byproduct of that is bilirubin. Bilirubin is conjugated with a glucose-like molecule. That I'll talk about that particular molecule here in a little bit. And that's actually how we can eliminate that in bile. Okay, so what kinds of enzymes, okay, yes, the enzymes are generally known as transferases, but what do we call the transferase enzymes that are specifically involved with glucuronidation? Well, it's kind of a long name. So we call those enzymes, see if I can put this up here. We call those enzymes, oh boy, here we go for some big words here. Uridine, so all right, uridine diphospho rather, diphospho alpha D glucuronic acid, all right. Glucure, oh, no. Okay, so uridine diphospho alpha D glucuronic acid, glucuronidation. Those are the specific enzymes involved, or we simply can call these UGTs. Okay, the UGT enzymes are what are ultimately involved. So these are the actual enzymes here, and then this word here in front, what does this mean? Well, this is a cofactor, if you will, that is required. These enzymes, just like many of the other enzyme systems, require these cofactors require additional molecules that help them work. So we'll just talk about that real quick, or a co-substrate, I suppose, is the best way of defining what this is. So this uridine diphospho alpha D glucuronic acid can be simplified to UDP, all right, or UDPGA, some people call them, but UDP. So UDP, okay, UDP is going to be the co-substrate, whereas UGTs are the enzymes. Now, the reason that we need UDP is actually converted into the modified glucose molecule, which is known as beta D glucuronide conjugate, or glucuronide conjugate products. So what I think I'll do here is I'll just draw, so this is converted into the actual conjugation product, the glucuronic acid product. So what I'm going to do is I'm actually just going to draw what that looks like. So this is ultimately what we're dealing with here. And it's a sugar, I'm going to draw it in its ring structure. I'm not going to draw the open structure, ring structure. And I'm going to give some three-dimensionality to it real quick here. So imagine that this is shooting back into the screen here. And there's an oxygen there. And you just have to basically, wherever points are, we're dealing with carbons. And then imagine that this is popping out of the screen toward you. So I'll make that a little thicker there. And this is popping out of the screen toward you here. All right, and then I have bond here. Okay, so just kind of imagine there's some three-dimensionality there. All right, so there we go. There's my ring structure, and I'll just draw the relevant structures. A hydroxyl group here. All right, a hydroxyl group here, and a hydroxyl group here. And then right up here, I also have COOH. Okay, so here we go. This is actually what we're dealing with, this glucuronic acid conjugate that comes from UDP. So this is actually what gets transferred to the xenobiotic or the xenobiotic metabolite, because in many cases, phase 1 reactions make the metabolites that come out of phase 1 reactions are more reactive and are able to enter phase 2 catalyzed pathways. However, that's not always the case. But be that as it may, this is the actual molecule that's being transferred. Now, if you look at it, you go, wow, that really looks very similar to a glucose molecule. And you could pop this thing open, and it would kind of have this fishbone-like, skeletal structure. My oxygen down there, or up there, wherever the heck you want it. And then you have your HOs, like that, something like that, right? You can imagine that easy. It looks like a sugar. So what differentiates this from the typical sugar molecules we're used to dealing with? Well, hopefully it should be pretty obvious, and that's because we have this group right here. This is a carboxylic acid group. So this is very acidic, and these carboxylic acid groups tend to have pKa values of around 4 to 5. So that means that you have about 50% ionization of this functional group at a pH of 4 to 5. But at physiological pH, and we'll just say physiological pH is somewhere around 7.4, give or take, depending on where you're at. So clearly this is much more basic, much more alkaline than a pH of 5. So it is going to make significantly more of this acidic group is going to be in its ionic form. Particularly, this is going to deprotonate. It's going to do what acids do in alkaline environments. It's going to lose its hydrogen, to the more basic environment, and so significant portion of this molecule is going to be in its anionic form at physiological pHs. And what does that mean? Well, it's large and it's charged. So what are you going to be able to do with large charged things? You're going to be able to pee them out. And that's really just like phase 1. That's one of the big things that the body's trying to do in biotransformation, is to make things more polar so you can pee them out for the most part. Okay, so let's go ahead and let me just give you an example. One example. There are many I could do, but let's just go ahead and give you an example of a common substance that we're used to, and that is a substance known as acetaminophen. Let me start over. There we go. So, acetaminophen, or paracetamol if you're not from the United States, from outside of the United States. Okay, acetaminophen. So, acetaminophen has the basic chemical structure that looks like this. Here it has an aromatic ring, or phenolic or benzene ring, as its central structure. So I'll attempt to draw that. I'll probably do a very poor job, so just kind of deal with it the best you can here. So you have this aromatic ring here. Bam. All right, and then I'll go ahead and draw the resonance structure in. All right, so there we go. And then out here I have a nitrogen, a hydrogen, and then I have, again, you just have to fill in the carbons. All right, so I have something that looks kind of like that, actually a lot like this. And then finally I have a hydroxyl group hanging off the other side of that benzene ring there. Easy enough. Hopefully you can can see that and see what's going on. I've got an acetyl group here, benzene ring, hydroxyl group. And then I have this, let's see, looks like a secondary nitrogen there. Okay, so what happens with acetaminophen, all right, there is a reaction, okay, that involves, so let's go ahead and make sure that we put the right enzyme. So the enzyme up top, all right, so that is going to be UGT. Remember, that's a transferase enzyme. And I'm also going to have my co-substrate, UDP, okay, because that's what's being turned into the glucuronic acid, the glucuronide conjugate. All right, so that gets converted into, let me just go ahead and draw this thing again. All right, there we go. All right, I'm not going to draw it with all the finesse that I drew the other one. I'm just going to simplify it a little bit, COOH, and then you can fill in the hydroxyl groups. Okay, so this guy is going to get attached to the acetaminophen molecule, and that reaction is catalyzed by the UGTs. And specifically, this is going to get attached over here. The hydrogen is going to get bumped off, and you have this relatively electron-dense area. Okay, oxygen atoms like to take electrons, so you have a a reasonably electron-dense region there. So this is nucleophilic. It's going to attract nuclei. It's going to attract this to be specific, and so this gets attached there. And let's just go ahead and draw what that will look like at the end of the day. So what I'm going to do is I'm going to put my metabolite, or my glucuronic conjugate here. I'm going to draw that first. All right, that's oxygen. Right, and so that is actually going to be attached to the acetaminophen molecule here. All right, there we go. And then let me draw my benzene ring. Maybe this is back behind you, if you will, so I'm not going to draw it quite as large. We'll put our resonance structure in there, and then our secondary nitrogen. Right, there we go. Okay, so what happened here is this hydroxyl group here, bump the hydrogen off. I had this oxygen here, and the oxygen, we attached this conjugate there. All right, so this is has undergone glucuronidation. And about 95% of acetaminophen biotransformation, 95, I think it's closer to 95% acetaminophen biotransformation is turned into this molecule here. This molecule is largely inert. It is not toxic. And it's only the other 5% that is transformed through other pathways into the NAPQI metabolite, which is toxic, that we're really concerned about. But anyway, this is just a basic introduction. Hopefully that made sense. Hopefully my rambling wasn't too bad and my drawings weren't terrible. So there you guys go. Hopefully you found that helpful. And maybe I'll do some more, a couple more videos, 1 or 2 more videos on glucuronidation. All right, guys, as always, thanks for hanging in there.